My name is Michael Blaine Hewling. I'm in Lab Section M06, and this is my video report for the Constant Velocity Lab. My observation was a tennis ball rolling across the floor, and the result was when fnet was equal to 0, the model in Python yielded a good result for what happened. As you can see here in the video, the tennis ball's there. I start the video shortly after the ball is rolled and stop it right before my dog picks it up. And that whole process lasts about 1.29 seconds. So as you can see, we have the origin here set at the center of the ball, moving in what is the positive x direction. And the screen is scaled using the diameter of the tennis ball, which is 0.067 meters. As you can see, the ball moves at constant motion across the floor, and it's tracked the whole way right up to the point where it's grabbed by my dog. We go over to Python, we plug in the ball's mass, which is 0.056 kilograms, the initial position of the ball, which can be found in using the tracker data. Then you can also use the tracker data to solve for the initial velocity, using delta x divided by delta t. Then you set your delta t in the program, set it relatively small to retrieve accurate data from when it's running. Set your time. The video ran 1.29 seconds, so set it to that. Fnet is equal to 0 because their ball is moving at a constant velocity, so all the outside forces on the ball are either not there or they cancel each other out, so that way it is allowed to move constantly. Then we plug in the motion equation based on Newton's second law, which is going to basically tell us how the ball should act. And when we run the program, as you can see, the ball starts at the origin and it moves slowly up, and as time increases, its position increases at a constant rate. Now, when you compare the data in Tracker, which is blue, and the data in Python, which is red, on the time and position, you can see that the data matches up fairly closely. So the program model was a very good representation for what actually happened to the ball. Now, the tracker data was somewhat offset from the Python data, but that could be due to other minor forces that weren't planned for in the tracker, or the fact that it was my first time using tracker and my plotting of the center of mass was not exactly great. So what does it mean? Is it possible to say how many pushes or pulls are added together to give the zero net force? Well, when you look at the x, y, and z coordinates, you can assume that there would be 6 pushes, or 2 going from each direction of the coordinate planes. Now, these forces could also be combined in a whole bunch of different varying ways, applying forces all from different directions of the ball. So there could be much more than 6, but just looking by the coordinate planes, you get that. And the reason the net force is still 0 is because though forces may be applying, like gravity or the force of the floor, they cancel out with each other, and that allows the ball to move at a constant motion, not accelerating or decelerating. What if? Wanted us to discuss briefly how the results would change and how they would remain the same if there was a different choice of origin. If a different origin were chosen, the velocities of fnet would remain the same, as in the actual motion of the ball would be the exact same. The only difference is that your starting point would change and your initial position would change, and your final position would change as a result of that, because your final position is based on your initial position and your average velocity, which isn't affected by its change in position, which we can see if we go back to Python. If we run the program again, but this time change the initial position to say 0.5, we can see the ball starts off from the origin, but still runs in the same path, just with a different ending point.